so we just watched the video with Professor Dave. We have weight versus mass. All right, so which one of these is a vector? Which one has magnitude and direction? Weight is a vector because weight has to do with gravity. So the gravity pulls us down to the ground. That means it has a direction. Weight changes according to time, which we'll put that down here in a second. But if weight is our vector, which one is our scalar? Mass. Okay. Mass is just a measurement. It's a number. Okay. So we don't have any direction with mass. Okay. All right. Which one of these changes due to location? Weight, because the gravity might be different, especially if you change location dramatically, like to the moon or something. Mass is mostly constant. I mean, barring some crazy weight loss program. Mostly constant. You may write down the definition of weight. If weight is a vector and changes due to location, huh? That's mass. Okay. So she just gave us the definition of mass. Mass is the amount of matter. Weight is the force of gravity on an object. Okay? All right. We needed units as well. Anybody remember the unit of weight? It's a weird one you might not have used before. That's our unit for mass. Well, those pounds are English units, so we won't actually use those in class. But weight uses the unit of newtons. Okay. So a newton is the force that it takes to move 1 kilogram of matter 1 meter per second squared. So gravity is actually an acceleration. What do you think of when you think of the word acceleration? You think of speed. You think it hit the skinny pedal, right? Like it's going to go faster. When you accelerate, you're going faster and faster and faster and faster. It's not a constant speed like highway speed you got cruise control on. Acceleration, you're going to continue. And so that's where the second, the squared comes in, is that we are continuing to move faster. All right, so we can tell something from the units. Weight is a derived unit. That means we had to do some kind of math to get weight, whereas mass is just a single unit. So we can just measure that. So that's an important difference. Mass is just measured, whereas weight is calculated. Okay. And so when you think about a calculation, we're going to think about a formula. Does anybody remember the formula from the video? F equals ma is where we get it from. Yep. Weight equals mass times gravity. So we'll write what that means. All right. And so our gravity on Earth (9.8 meters per second squared). And you know what? On Earth, it's not even always that. So let's kind of look down in the Canvas lesson. Well, before we get to the on Earth part, we'll look at this picture here that's embedded in your lesson. On Earth, an average sized person that has a mass of about 63.5 kilograms, so they weigh 140 pounds. Okay, that's okay. So on the moon, if on Earth you weigh about 140 pounds, on the moon you would only weigh about 23 pounds. Right, because the gravity on the moon is only 1.6. Okay, whereas on Earth it's 9.8. But on Jupiter, that same person, the same 140 pound person, would weigh 365 pounds. So, I mean, you want to think about, like, we talked a little bit about astronauts in space, but let's kind of imagine, what if people actually did, say, go to Jupiter? Like, how would your body react to that? It would be a lot harder to move around, for one thing, right? Because 365 pounds is a lot more weight to carry. All right, now I know you can't stand on the surface of the sun. I get that. But if you could stand on the surface of the sun, that same person would weigh 3,914 pounds. So, like, why is that, though? But why does it have a high gravity? Has a high mass, because a greater mass has a greater gravity. That's true, because we said the definition of mass is the amount of matter. So the sun has a much bigger amount of matter than the Earth does. All right, so back to the Earth. We're back on the Earth again. If we come down here in the lesson, I'm going to pull the camera away for a second, to this simulation here. Let's kind of go to that real quick. When you click on that simulation, it takes you to the physics classroom, so we're grateful for them. But let's look at right on the equator. Let's find one right on the equator. So in Singapore, the gravity of the Earth is 9.776. That rounds off to 9.8, right? Yeah. But in Greenland, Iceland, over up in the top, Greenland, we are 9.839. But we're on the same planet. So even on the surface of our Earth, gravity changes a little. Changes just a little bit. So down here in South America, we have 9.767. So still rounds off to 9.8. But you can see that on Earth, the gravity does change just a little bit. Yes, sir? How did they measure this? How did they measure it? You mean, how do they measure it? How do they know? Lots of fancy calculations. But also it has to do with the distance from the center of the object. So the equator is the furthest from the center, those kinds of things. That has to do with a couple other things too. But it is interesting to see that on the face, even on just the face of our planet, the gravity is a little bit different as we move over it. All right. So even on the surface of our planet, gravity is just a little different. Let's talk a little bit more before we get to our submission questions. I know you're like, I am done talking. I hear you. But gravity. If we said that weight is a function of gravity, weight equals mass times gravity, let's talk about the gravities in a couple of places. We already wrote the gravity of Earth. But what about on the moon? 1.6. Yep, we said that one. And what about on Mars? Do you think Mars is a third the size of Earth? Is it going to be bigger or smaller than Earth's gravity? Smaller, right, because a smaller mass is going to have a smaller gravity. So, right? And let's look at the biggest planet in our on Jupiter. It's 20. Wait, I totally wrote the wrong number. 24.9 24.92. I know that looks great. Meters per second squared. 24.92 meters per second squared. So let's say, let's kind of think back about that picture so we can have an example. If we have an average person, and we will just say that that average person is about 70 kilograms, okay? 70 kilograms. Are the kilograms going to change no matter where we put this person in the universe? No, because that's the mass. So good job on that one. But their weight will change. So we're going to practice their weight on Earth. You're going to do a problem like this for your exit ticket question here in a second. But weight on Earth equals mass times gravity. So we're going to say 70 kilograms times 9.8 meters per second squared. And then I can't do that math in my head, so I'm going to pull up my calculator and say 70 times 9.8 equals 686. What unit is that? Let's come back up in our notes and look. Kilogram over meter, kilogram times meters per second squared is a Newton. So it's newtons because we did kilogram times meters per second squared. So it's newtons. So I think I'll stick with my pounds, but 686 is a really big number. Newtons is just a different unit. Mitchell, you're not taking notes, dude. Okay, so on the moon, mass or weight is still going to be mass times gravity. So mass times gravity. Our mass doesn't change. Okay, our mass is the same. But the moon's gravity is 1.62. So let me pull back in our calculator. I'm going to say 70 times 1.62, 113.4. Okay. I like the moon's number way better, but newtons is a different unit. So we're not saying pounds. We're not, the 70 kilogram person isn't 686 pounds. That's not correct. It is newtons. That Newton unit is really important. What would it be on Jupiter? One last one, and then I'll kind of instruct you on. We're still going to use mass times gravity. That's always going to be how we find weight. We're still going to have the same mass. That won't change. The person's flying around in a spaceship. Their mass doesn't change. And Jupiter, 24.92 meters per second squared. So again, we pull back our calculator. $1,744 newtons. Okay. Give me a thumbs up if you feel like you can do those calculations. Okay. That looks... Really? Maybe? I think maybe we're this way a little bit. Maybe. Okay, maybe we'll come and check on you. All right, so this is exactly what you're going to be doing for your exit questions. You're going to be given a mass, and then you have to figure out what is the weight in newtons on Earth and what is the weight in newtons on Mars. So let's kind of look at those exit questions, and we will kind of look at them. So these are the 3 questions you're going to submit for today. If an elephant with a mass of 1,090 kilograms were on Earth, what would its weight be? So you're going to go weight, mass times gravity. So we're using the 1090. So it'd be 1090 times 9.8. Put that in. If the same elephant, so 1,090 kilograms, were transported to Mars, we're going to use Mars. what would its weight be? It's still going to be mass times gravity. And why is gravity different on Mars? You just have to explain that in a sentence or two. And then CK12. So I will leave those questions on the screen for you.